This is not a numerical linear algebra course, but in practice, all linear algebra is done using computer assistance. Real-world matrices don't tend to be small, and you can imagine that doing Gauss-Jordan elimination by hand on even a 10 by 10 matrix, for example, would be a wretched experience. In this video, we discuss some numerical aspects of Gaussian and Gauss-Jordan elimination. In particular, we look at the speed of the algorithm. For this, we need a brief definition. A flop is an addition, subtraction, multiplication, or division. And we measure how fast an algorithm is by counting the number of flops it has to perform. For example, suppose you were to perform Gaussian elimination on the following matrix. We'd multiply the first row by -4. That's 3 multiplications, each of these being multiplied. So that's 3 flops. Then we add and that's another 3 flops. 1, 2, 3. For a total of 6 flops to go from here down to here. We will make the observation that the forward phase is much slower than the backwards phase when we're performing Gauss-Jordan elimination. This is because when we're doing the backward phase, a large number of entries in the matrix are already 0 and can be ignored. So, for example, suppose you wanted to perform Gaussian elimination on this matrix. We're not going to do this. That would be very tedious to do by hand. Let's just ask ourselves, how many flops does it take to turn these 4 numbers to 0? Well, to get rid of this 2, you'd multiply the first row by -2 and add it to the second row. That's 6 multiplications and 6 additions for 12 flops. Another 12 flops to get rid of this 4. Similarly for this 3 and this 4. 48 flops in total. Now suppose you have a matrix of the same size in row echelon form. This is a different example. It's not what you get by performing Gaussian elimination on this matrix. Let's ask ourselves how many flops it takes to turn everything above this 1 to 0. We start by multiplying the last row by -4 and adding it to the 4th row. At first glance, that might seem like 12 flops, 6 multiplications, and then 6 additions. But in fact, you can ignore everything to the left of this leading entry. We multiply these two numbers by 4, and we add them to these two numbers. Sorry, what am I doing? We multiply these two numbers by 4, and we add them to these two numbers. And this 4 turns to 0, and this turns to -16, and those are the only numbers in this row that change. So that was 4 flops, 2 multiplications, and 2 additions. Likewise, it takes 4 flops to get rid of this 6, 4 flops to get rid of this 5, 4 flops to get rid of this 2, for 20 flops total to get rid of everything above this 1. The first part of the backward phase. Compare that to the 48 flops it took to do the first part of the forward phase. In general, if we're performing Gauss-Jordan elimination on an n by n plus 1 matrix, the forward phase requires about 2/3 n cubed flops, while the backward phase requires about n squared flops. This is the size of the augmented matrix if you have n equations and n unknowns. If you were wondering why we're interested in those particular numbers. So, for example, say we have a 50 by 51 matrix that we're performing Gauss-Jordan elimination on. The forward phase requires about 2/3 times 50 cubed, or about 83,333 flops. By contrast, the backward phase requires on the order of 50 squared, or a mere 2,500 flops. In this video, we discussed the speed of Gaussian elimination and Gauss-Jordan elimination. We found that the forward phase of the process, that is, the Gaussian elimination, requires on the order of n cubed flops, while finishing the Gauss-Jordan elimination by performing the backward phase is then much quicker.